Alright, now I'm going to show you another use for VIR charts, and that's finding the internal resistance of a battery. So a pure or ideal voltage source is called an EMF, or electromotive force. And that's a fancy way of saying the thing that shoves electrons. So if you're shoving an electron, there has to be a force, because a force is any push or pull. And so if you have pure voltage with no resistance, it's an EMF, or electromotive force. Real batteries are not ideal. They do, in fact, have some internal resistance. So the terminals have a resistance, like the ends of the battery, they offer some resistance. The actual chemicals in the battery offer some resistance to electrons moving. And we call that the internal resistance. So the terminal voltage, or whatever actually comes out of the battery as far as its voltage, is different from the EMF inside the battery. And the way we deal with this is we basically pretend like the battery has a resistor stuck on one side of it. And that's how we can deal with the fact the battery is not a pure voltage source. It does, in fact, have metal that's resisting and chemicals that are resisting the electrons moving. And you'll often be asked to find, well, what is the internal resistance of the battery? And let me show you how you do that. If you need to copy down these notes, please pause to do that now. So here's an example question. A battery has an EMF, so a pure voltage, of 9 volts. But there's an internal resistance in that battery of ½ an ohm. What is the terminal voltage? So this is the way of asking what really comes out of the battery. Terminal voltage is what really comes out when the battery is connected to a 20 ohm load. Alright, so we'll basically use a VIR chart to do this. Here's the general rule though. The terminal voltage on a battery is equal to the EMF, or what I will abbreviate with a curly E. So the voltage, if there's no internal resistance, the pure voltage of the battery, minus the current times the battery's internal resistance, which we use a little r for. So that's terminal voltage equals EMF minus current times the resistance inside the battery. And I'll basically just do this with a VIR chart. I will pretend that the battery has a resistor stuck to it. And that will be the battery's internal resistance. And then we'll have the rest of our circuit. We said it's connected to something with 20 ohms. And now this part up here is the battery itself. We have 9 volts coming out of the EMF, the pure kind of imaginary ideal, and a 0.5 ohm resistor right here. Now we'll just make a VIR chart for this. So this time we'll have little r, the battery's resistance, and then any resistors out here, R1, we could have more, and then we'll call the pure resistance the curly E. So we've got little r, let me start over, little r, R1, and the pure resistance, or the pure voltage from the battery. Okay, and we'll do V, I, R. So that pure voltage, 9 volts. And little r has a resistance of 0.5 ohms. Big R has a resistance of 20 ohms. And so our equivalent resistance, which will now go here, since this is a series circuit, 20.5 ohms. Well, now I can easily find the current, and since this is a series circuit, current will have to be the same anywhere. 9 volts divided by 20.5 ohms, and I get 0.44 amps. Since this is a series circuit, everything will get that 0.44 amps. And so the voltage across resistor 1, 20 times 0.44, gives me 8.8 volts, and 0.5 times 0.44 gives me, rounding, 0.2 volts. Okay, now we can use the equation I gave you up here. V terminal equals EMF minus I times little r. My terminal voltage, the thing I'm looking for, just leave it as a variable, E is 9 volts, minus I times little r, which is just the voltage across little r, minus 0.2 volts. And I get my terminal voltage is 8.8 volts. You might be wondering, could we have just picked it out of here? If this is the only resistor, yes, but that won't always be the case. This is the general safe way to do it. Terminal voltage is EMF minus I times little r. And that's how I did that. One more example. All right, next one. A battery with an EMF of 6 volts is connected to a 100 ohm load. The terminal voltage drops to 5 volts. What is the internal resistance of the battery? So let's draw this. I'm going to have my battery, and I will pretend there is a resistor. Out here we've got a 100 ohm load. Okay. Now remember, all of this up here is what we have before today considered the battery. Its electromotive force is 6 volts, that's little e. We are looking for little r, its internal resistance. But we know that the terminal voltage, meaning from here to here, is 5 volts. And that means that this 100 ohm resistor is getting that 5 volts. So let's make a VIR chart and see if that information helps us. We have little r, let's call this big R1, curly E, VIR. So I'm using this because a VIR chart is, once again, if you're not sure what to do, you can always just refer to it. Well, we know the voltage on E is 6 volts. We know big R1 got 5 volts. Now, since this is a series circuit, that would mean that little r had to get the rest, 1 volt. We know there's 100 ohms of resistance on R1. So we can easily find its current, 5 divided by 100, 0.05 amps. And since this is a series circuit, that's going to be true everywhere, 0.05 amps, 0.05 amps. That means that the R for little r1 would be voltage divided by current, 1 divided by 0.05. This thing has an internal resistance of 20 ohms then. Just doing that division using V equals IR, solve for R. And that means the equivalent resistance, which now goes here, 120 ohms. And we could confirm, if we divide 6 by 120, we do in fact get 0.05 amps. All right, so the question was, what is the internal resistance of the battery? Well, I just found it, 20 ohms. All right. Any questions? Text, call, watch the video again. And I'll see you tomorrow.